created from stolen code from another company, but using binary images alone. And what they've done is, in their white paper, you'll see all kinds of statistics that they ran on FTP clients that show similarities based on API call structures between similar software. It's pretty cool stuff, and it's been demonstrated to be effective. Halvar, as we mentioned earlier, both his bindiff tool and VX class help create lineage between malware samples through identifying similar areas of functionality. And there's a number of others in this space, so apologies if anyone's in the crowd and you've written about this. I unfortunately don't have time to go through everyone. Okay, so how can we use this for attribution? Well, the obvious use case is through reuse of code functions. So this is particularly useful for closed source projects where we don't necessarily have access to the source code, where we're pretty sure that the malware is not based off of any kind of commercially available malware kit such as Zeus. And it's very good for tracking the progression of malware and related malware as people further develop malware. You know, most of the malware that we see out there on the internet today are derived from stuff that we already know about. So through being able to track this lineage and spot individual cases where we think the code is completely unique, it really helps us narrow down our efforts in terms of performing more manual analysis. A lot of malware, though, as we mentioned, is based off of kits like Zeus, so it has limited application in that space. You know, if we see two pieces of malware on the internet that are both based off of Zeus, even if they're different versions, they may be different people, they may be the same person. All that really tells us that there's two people on the internet that have both bought the Zeus framework. So that it doesn't help a lot in cases where we're dealing with something like the Zeus platform. Something that I started looking at pretty heavily is how we can perform analysis of the quality of code. And as far as I know, this hasn't been used in the past for analysis of malware. I'm happy to be wrong, though, if anyone knows otherwise. But there are a few examples here of things that we can potentially observe to try and tell us something about the skills of the programmer. The first is nested statements. Anyone that's tried to write C will know that creating heavily nested conditional statements and loops is something that every novice programmer does. Some nesting is unavoidable in a complicated program, but through analysis of heavy levels of nesting, we can potentially determine something about the skill level of the author, and we have some statistics on that in a few slides' time. Things like unclosed files, file handles are often an indicator of a sloppy programmer. Memory leaks, almost every program has some of them, but an excessive level of memory leaks, again, is another indicator potentially of a sloppy programming effort. Redundant functions, multiple functions that get called but replicate each other's functionality is something that, again, may tell us that the programmer has written the malware through maybe patching lots of different pieces of code together from lots of different places and hasn't really looked at the individual functionality and stripping out the redundant functions there. And that's something that we could potentially automate through the use of API call analysis to determine the functionality of a given piece of code and therefore identifying redundant areas of code within that program that perform similar functions. And debug strings being present, again, this is something that I think Greg mentioned this morning, is another thing that we can use, number one, to potentially attribute us to a given individual, but also shows us that the individual didn't have an awareness that he or she was compiling these debug strings into their code, again, which may tell us something about the level of skill that they have. So here's an example of a nested conditional, which can be easy to spot with the naked eye. But in a second, we're going to have a look at how we can automate identification of similar nested statements. As we mentioned, PDB symbols can often tell us, lead us to the identity of an individual. There are numerous cases where I've spotted an individual's username or even their real name, where their Windows username was first name.last name, in the PDB file, and they just compiled it into the program, not realizing that that reference was there. It can also tell us things about like the operating system that they're using. For example, if they're storing, if you're using Microsoft Visual Studio, the default location for all your projects is going to be My Documents, Visual Studio, 2010, 2009, whatever. And that's therefore going to have either C users or C documents and settings, which will tell us whether you're using XP versus 7 based on those directory structures. So there's all kinds of neat stuff that we can pull out of debug symbols in the code, in addition to telling us that they didn't really know what they were doing for leaving them there in the first place. So here's an example of Stuxnet, which actually did have a PDB symbol left in it. However, I don't know how well everyone can read that. It isn't really anything that gives us much data. And if you do a little research into the PDB string, you'll see that, and this is one for all of the conspiracy theorists out there that like speculating a little. Myrtus is a botanical reference. And guava is actually a plant which is in that botanical family. I'm not a botanist, I just did some Googling here. And so it turns out that there's a whole bunch of plants which are in this family. They start off at myrtle, clove, guava, allspice, and the final one is eucalyptus. So the fact that they've left this there, most analysis of Stuxnet, anyone that you talk to will probably tell you that they were relatively skilled. The fact that it exploited a zero-day vulnerability in link files tells us something. So perhaps they're trying to tell us something through this debug string, that there are more variants to come, and perhaps the last variant is going to be eucalyptus, which, by the way, is the plant that was commonly attributed to being the burning bush in Exodus. So maybe the last version is going to be super destructive, who knows. Okay, so I'm going to talk about automation for a little while. So automation is really, really important for scale. Anyone that's run any kind of incident response group analysis organization will tell you that one of the big problems is the volume of information out there, the volume of stuff that needs analyzing far outweighs the number of skilled reverse engineers which are available to most organizations. So some level of automation is very, very important to help us scale that response capability. So too much badness, not enough analysts. And those analyst times are probably better spent on edge cases, on things that we can identify are really of interest to us, rather than repeating the same 5 boring procedures again and again and again just to identify that something is derived from something that we already know about and therefore isn't of any interest to us. So one of the first examples of a technology that can help us with that is isomorphic analysis. We already discussed that, being able to create lineage between what we know about and what might have changed within that program, and then just performing analysis of the change parts. And then cataloging of those identifications and markings so that when we see them in the future, we don't have to manually go and look at a database of tool markings that we know about and compare that to the target that we're analyzing, that can happen in an automated fashion. So BlackAxon is a work-in-progress tool which I'm posting a link for at the end of the presentation and will be posted after the conference. It's been designed as a proof of concept just to demonstrate how some of these various components can be automated. It's basically an IDA plugin that's using debugger breakpoints and some static analysis to tell you various things about the binary. And because of that, it does mean that malware that has any kind of debugger detection right now can detect it. There are obviously some things that you can do to prevent being seen, such as catching the is debugged API call and making that return in a certain way. But right now, out of the box, you're going to get seen. One of the important concepts of this, though, is that the user sets the rules. I'm a strong believer that different adversaries are interested in different, or rather different end users, are interested in being able to identify different attributes in different malware. So for example, a defense intelligence agency might be more interested in spotting certain attributes in malware that they know are associated with an organization they're interested in, such as a Chinese nation-state sponsored organization. A bank may be interested in spotting traits which are more commonly associated with organized crime and so forth. So it's basically an XML-driven model that allows you to create your own flags, things to look for that you're interested in, and add your own weighting around those, and add your own definitions of how important those things are to you to look for. And so I was originally going to do a live demo, but I think that lots of little text on screens, unless you're popping shells and everyone claps, are completely boring. So for those of you that like little text on the screen, this is an example of the plugin running. What it's basically doing is performing analysis, looking for nested loops within Stuxnet. And there's an example up there of a return from a nested statement. But this is what I think is really cool. I did some analysis using the plugin of various commercially written software against various malware, and this is what we came up with. The higher the score, the less nested statements we found. So basically you have calc.exe to begin with. Secondly, you've got a control which I wrote, which was just some C that has heavy levels of nesting in it. You then got netcat, Stuxnet dropper, Firefox, new war malware, NIMDA, and configure. Now, this doesn't necessarily immediately tell us the skills of each of the individuals that wrote these, because obviously in cases of things like Firefox, multiple people were involved in that process. But it's one metric which we can start to use. It tells us a little more about the adversary and starting to read between the lines in telling us more than just, well, this piece of malware modifies your registry keys, great. You know, it starts giving us more information that we can start building on to, going back to the analogy I used earlier, tell us the kind of firearm maybe that was used to shoot the bullet rather than just that the guy was shot. The other thing that it does is allows you to define chains of API calls. So what we're looking to do here is not just identify what a particular piece of malware does, but how it implements that. So in the first case here, this is an example of persistence where we have two techniques for injecting a DLL into processes. So in the first case, and the first one is very commonly used, configure uses this, where we basically get a list of processes through using the create tool help snapshot. Then we use we get the list of the first process and then walk the tree, and then open the process and write to the memory. In the second case, we have a separate example where a piece of malware creates a new process and creates it in a suspended shape, which I think is the sixth parameter to create process. What it then does is virtual alloc, which creates some memory within that process space, and then we then write to the memory area, which injects our DLL. So these are two different techniques which, similarly to the application exploitation matrix that we looked at earlier, we can use to score not just what the malware does, but the merits of the techniques that they use to implement that functionality. There's a second example here where we, again, these are very basic, but where we have some update functionality within the code. And in the first case here, we have actually an example from configure where we have URL download file. It performs a read, then an XOR to decrypt that file, and then it creates process. So we have evidence here of an encrypted update functionality, which we can use as a signature. On the second hand, we have just simply using URL download file and then create process. So it's unlikely that this is going to be an encrypted update. Again, this is something that we can use to score malware. And one of the things that I'm going to be working on over the next month is publishing more signatures like this that we can use to start profiling the techniques and modus operandi that are used by an adversary for implementation of a certain piece of malware. So one of the things I'm unlikely to do for a while, if ever, unless someone pays me full time to do it, is develop this as more of a commercial product. And the way that you might do that is using something like detours hooks or kernel hooks to identify the hit points that you want, the calls to the API functions. And the reason that you do it this way is basically to allow you to sit lower in the operating system, so you're less likely to be detected by the malware. And through using a mechanism like this, you could potentially deploy the software on a lot of nodes across a bunch of workstations and then look for certain behaviors in that manner.